My dear friends, welcome to Rajshekhar classes on applied data science with Python. This is lecture number 592. In this lecture, we will try to understand CPUs versus GPU for deep learning. Let me introduce you to something called GPU because lots of deep learning code in reality is executed on GPU and not on CPU. We all know what is CPU is. CPU is literally is a computational unit that we all use in any modern computer. Let me explain you what is GPU, how it is different from a CPU, and why we need GPUs for deep learning. So GPU stands for graphics processing unit, and CPU is, as most of you know, central. What is CPU? Central processing unit. The word graphics here tells you a lot about what GPU does. GPU become very popular in late 90s and early 2000, isn't it? They are mostly used even today. GPUs are extensively used for gaming. If you play any high-end game on your laptop or desktop, you will need a GPU, as gaming is very computationally intensive, isn't it? Yes, gaming is computationally intensive. Just imagine you have to render lots and lots of dynamic video on your screen. In the context of gaming, what you have to do, you have to render lots and lots of dynamic video on your screen. So gaming requires lots of computational power. Realistic 3D gaming requires lots of computational power, and that additional computational power actually comes from GPUs, isn't it? Even though GPUs are initially built for gaming, GPUs are initially built for gaming consoles. They become extremely popular tool in deep learning. I will show you why. What is the reason behind it? Let's understand the high level architecture of a CPU and GPU. Let's understand the difference between both of them. In a CPU, you have your if you go through the CPU, what happens in CPU? You have RAM like this. You have your RAM here. Just generally we used to say 64 GB of RAM, 4 GB of RAM extra, isn't it? This is not your hard disk. This is your RAM. Now your CPU is here. Let me say your CPU is here. This is, let me assume this is my CPU. Your CPU is here. Your RAM has all the data. Your CPU is here. Within your CPU, you typically tend to have multiple cores in modern CPUs. Let's assume I have 4 cores, isn't it? What are these? I am assuming there are 4 cores: core 1, core 2, core 3, and core 4. They are first core, second core, third core, fourth core, isn't it? In multi-core CPU, so each of these are core, isn't it? First core, second core, third core, like that. In a multi-core CPU, you can have 4 computational units that can run in parallel. Maybe your first core, your first core may useful for playing songs, and your second core may be useful for browsing internet. Your third core may be useful for watching a movie, isn't it? Your fourth core may be using something on YouTube. Probably that can be rendered using other. There are 4. I'm assuming there are 4 cores. Each core is performing different tasks. So these cores can work in parallel. All these cores, core 1, core 2, core 3, core 4, can work in parallel, and this space in between is called, what is this? This area is called cache, isn't it? What is this? Just see this particular area is known as cache. Just observe this one. This is my cache, isn't it? I can say this is a cache memory. This particular area is called as a cache. All this is on single chip. Just see this one. What is on single chip? First core, second core, third core, fourth core, and cache. All of them are on single chip. The RAM and CPU if you observe here, the RAM and CPU are connected through motherboard. Your RAM and CPU are not on the same chip. Your RAM is outside the chip. Cache is like on chip memory. What is this cache? I can say cache is a single chip. Therefore, I can say cache can be treated as on chip memory. Typically, much smaller than RAM, isn't it? What is the size of cache? It is size of cache is much smaller than RAM. So what it does is, the closer you are in each of your cores, just see this cache is very close to all the cores. The fast as this cache is close to first core, second core, third core, therefore the faster you can access that cache memory through the cores, isn't it? Core 1, core 2, core 3, core 4 can easily access cache memory. Suppose if I am trying to do this operation, let's say I have matrix here. Let me assume I have matrix A. Suppose I am trying to do this operation. I have matrix A and I am trying to multiply with vector B. This is matrix A and this is vector B. I have matrix A and vector B, isn't it? Now let me assume this is what is this? This row is A1, this row is A2, this row is A3, so on and so forth, isn't it? Let's call this matrix is B, column vector, multiplying both of them and get a result. If I multiply both of them, I will get result. First entry in result matrix is A1B, second entry is A2B, third entry is A3B, so on and so forth, isn't it? So what happens is, because B used in B, just observe, because your B, capital B, is used in this computation every time. B is being used in every time. That is important. B is being used in every multiplication because it is being reused so many times. Just observe this one. Your B is reused so many times. It makes sense. It makes sense to store capital B in the cache. So I will store capital B in the cache and some parts of A also stored in the cache. Since cache is on the same chip, cache is also memory, isn't it? Cache is also memory literally, isn't it? Since this cache memory is on the same chip as the CPU, the processors or the cores can access this much faster than RAM, isn't it? These processors or cores can access this much faster than RAM. So whatever you are reusing more and more, you typically tends to store. Where will you store? What typically tends to store in cache. This is how it works. This is your simple CPU, and simple CPU can process 4 parallel tasks, which means on this core 1, what I am doing? On this core 1, I am multiplying A1 and B. On this core 2, you could running A2 multiplied with B. On the core 3, you could run A3 into B, and on this fourth core, I can multiply A4 and B. And once these multiplications are done, you can multiply A5B, A6B, A7B, A8B. You can do it parallelly, and your B is stored in cache. Not only B, parts of A can also stored in cache memory, isn't it? Stored in cache here. Let's A5B, let me say A5B is not available in the cache. It will bring it from RAM. This is very high level overview. There are lots of intricate details for each. I have to teach you all our computer organization and microprocessor interfacing, which spans 2 to 3 semester courses. I gave you a very high level overview here. What GPU does? GPU is very different. This is how CPU operates. Let me finish CPU here itself. So what's happening is, at any one instant of time, what happening in the case of CPU, at any one instant of time, A1B, A2B, A3B and A4B isn't it? A1B, A2B, A3B, A4B are being run parallelly. All 4 can run parallelly because I have 4 cores. If I program carefully, if I use multi-threading, I can do it. Then after that, what I have to do? A5B, A6B, A7B, A8B can be run in second timestamp, isn't it? In first probably probably A1B, A2B, A3B, A4B, A5B, A1B, A2B, A3B, A4B probably takes 1 millisecond of time. Once these are done, in second millisecond of time, I will run A5B, A6B, A7B, A8B. That's important. So on and so forth, isn't it? But at any time, parallelly, I am running 4 tasks. So 4 parallel tasks. CPUs are designed for general purpose programming, isn't it? Just see, in first core I may play music, on second core I may view YouTube, on third core I may do some sort of maths, on fourth core I may execute some sort of MS Excel related things. CPUs are very general purpose computational units, and CPUs are very fast. Typically you see things like 2 gigahertz basically says how fast this CPU can operate, how fast it can compute. Typically we have 2 to 4 gigahertz processors today. Now let's go to GPU. GPU has a very different architecture. Let me explain let me explain about GPUs in my next lecture, that is in lecture number 593. Thank you very much.